Analysis of variance. And the idea is we are looking at a numeric variable. Okay. And the measurements will exhibit variance. Okay. Sorry. Okay. And what we're trying to do is we're trying to break apart this variance based on the group from which our measurements came. Try to quote. Break down the total variance based on group from which measurement came. So, for example, perhaps we have three groups, okay? Yeah, we just group 1, group 2, group 3. And you know, group 1's measurements were whatever, and group 2's measurements were whatever, and group 3's measurements were whatever, okay? Each of these groups will have a sample mean, okay, and a sample standard deviation, and a sample size. Okay. So I guess technically it would be y bar 1, y bar 2, y bar 3, s1, s2, s3, etc., etc., etc. Okay. If we looked at all the measurements together, okay, we would have a total of n1 plus n2 plus n3, and this is we call it n dot, okay? Total of n dot measurements. Okay, the dot representing all subscripts, right? So if you have 7 groups, this dot means n from all 7 groups or whatever it might be. Dot. Okay. And then we would also have what we call the grand mean. Okay, which is y double bar, and this would be the sum of all y's divided by n dot. Okay. This is, note that this is not equal to the average of y bar 1, y bar 2, and y bar 3. Okay, you can't just take y bar 1, y bar 2, and y bar 3 and average them. You would have to add up all of the data points together. Okay. Now, a lot of times when you do these analyses, you don't have access to all the raw data points. So another way, you might just have the summary information. So y double bar can also be found doing n1 times y bar 1, and this would give you the sum of everything in group 1, plus n2 times y bar 2 plus n3 times y bar 3, oops, all divided by n dot, okay? Or the generic form would be n times y sub I over n dot. Okay, so when we throw all the measurements together, we've got the grand mean and n dot for the total number of all the data points. Today is the 20th. Whoa. Okay, let's see. Okay, so let's get back to this concept of analysis of variance, and let me use an example from our textbook. Okay, so let's see, where is it going to be? Okay, let me zoom in on this. So I'll let you guys, if you want, you can. Alright, so this is the data that we're going to use for our example. Okay, there are, what we did was we put different lambs on 3 different diets of food. Okay, and we call them diet 1, 2, and 3. And we had a total of 12 lambs. Okay, so under diet 1, one of the lambs gained 8 pounds, another lamb gained 16 pounds, and another lamb gained 9 pounds. Okay, and under diet 2, this is how much the different lambs gained weight, and under diet 3, this is how much the different lambs gained weight. And then those summary statistics being the n, the average or the y bar for each diet, and the standard deviation of each diet is also provided, as well as the sum of those. But I guess that's just to show to get 11 you do 33 divided by 3. Okay. Let me close that. Sorry, let me just zoom out here. Okay. I'm going to now plot these Okay, and here I'm gonna create a dot plot with all points. Okay, all three groups together. And the smallest one is 6 and the largest is 21, so I'm going to kind of just start it here at, maybe I'll move that lower. 5, 6, 10, and then maybe I'll just copy this. Okay, so I'm just gonna throw all of these dots here. Okay, so here is the lamb that gained 8 pounds. Here's the lamb that gained 16. This one gained 9. Okay, and then another lamb gained 9 pounds. And another one gained 16 pounds. And here's one that gained 21. And this one gained 11, and this one gained 18. And then this one gained 15, that one gained 10, that one gained 17, and this one gained 6. Alright, and so this is all 12 data points. And so we would say, you know, there's variance among, we have total variance, right? There's variance between the amount of weight the lambs gained, okay? So we observe variance between the different amounts of weight gained by the lambs. And so the question we have is, did they gain different amounts of weight simply because all lambs are different, and even if you gave them the same food, they would have gained different amounts of weight? Okay, so because we know in life everything's a little bit different, and so would they have shown kind of this much variation, or is can the variation be partially explained because we had 3 different diets? Okay, or I shouldn't say 3 different diets, but can it be partially explained because the diets were different? Okay, so is the weight gained, you know, by one of the diets at least statistically significantly different from some of the other ones? Okay, so we're asking, did the lambs exhibit different weight gain simply because of individual differences, or can some of the variance be explained by the existence of multiple diets. Okay, that's what we want to know. And so we're going to perform a hypothesis test, okay? And this is ANOVA. This process or this method is analysis of variance, okay? And the one that we're going to learn in detail is called Way Anova, okay? Okay, we're Way Anova. This is the simplest form of ANOVA. If you take more statistics classes, you can take an entire course on ANOVA. It probably goes hand in hand with a class called Design of Experiments. So you might take a class called Design of Experiments / ANOVA or something, and you'll cover all sorts of methods. Okay. In our class, we're going to cover Way Anova in detail, and I'll briefly mention some of the other forms of ANOVA, but we won't cover those in detail. Okay. So this is Way Anova, and basically we have one numeric variable, which is our response, and we're trying to explain it by the existence of a categorical variable. Okay. One numeric response, okay, and we try to explain the variance in the response with a categorical variable. Just slide this up and okay, I want to keep the that up there. Okay, and so our null hypothesis for Way Anova is that the different groups do not explain any part of the variance, or do not explain the variance in our observations. Okay, or symbolically, we would write the null hypothesis is that the mean of group 1 is the same as the mean of group 2, which is the same as the mean of group 3. The alternative form, or alternative hypothesis, is that at least one mu is different from the others. Okay. There's also an alternative method of writing hypothesis symbolically, okay? alternative form of hypotheses. Okay. And first I have to explain that in this form, in our model, each data point y sub I, okay, has its particular value because of the overall mean of all data plus the effect of being in a particular group. It's a tau. A tau. It looks like a T, but Greek. So let me label all of these things. Okay, so each value of y is the sum of the overall mean in the population. So notice these are Greek letters, meaning these are population, not from our sample. This is known as the effect of being in a group, and this is individual differences, also called residuals. Okay. So for example, if we were talking about how tall someone is, okay, under the null mod, under this form, we would say we could say people are different heights, and part of that height difference can be explained by their sex. So if you are male, the average height for male is this, and then there's individual differences. And if you're female, the average height for female is this, plus individual differences, which may be positive or negative. Under this form, it's very similar, except rather than saying this is the average for men and this is the average for women, we say here's the average for all people. The average height of all people in the US maybe is 5'7". I'm kind of making that up, okay? And I'll say if you are male, by virtue of being male, we're going to add 3 inches so that your group average is now 5'10". Whereas if you are female, we're going to subtract 3 inches so that your group average is now 5'4", okay? And then plus individual differences. Okay, and so you might be tall compared to other males, or you might be short compared to other males, or whatever it might be. So this could be plus.
Would it have a numerical value then?
So yeah, everything here is numeric.
Right.
Yeah. So if we were talking about heights, this might be 5'7", so 67 inches. And then we'll have either +3 or -3, depending on the group you're in, plus whatever. Any number from, negative, negative 60 to positive whatever, based on individual differences. Probably, whereas where most people are going to be, between plus or minus 6 of this. Okay.
And so that number will be different for each individual one?
Yes, each individual person will have a different, what we call residual, because just saying men and women have different heights doesn't explain everybody's different height, okay? There's lots of things, but if we just had a simple model and said people are different heights partly because of their sex, then this would go in there, okay? The simplest model would just be the overall mean plus individual differences and just say everybody's different, okay? But we can, at least for height, we can explain part of it and say part of it is due to sex or gender. Okay. So with the alternative form of the hypothesis, the null hypothesis would be that tau 1 is equal to tau 2, which are both equal to 0. Or tau 1, tau 2, and tau 3. Basically, all taus are equal to 0. And then the alternative is at least one tau is not 0. Okay, so both of these are effectively saying that the mean of each group is the same as the population. Okay. I present both of these because I think this is conceptually easier to deal with, but this only works for Way Anova. Okay. In more complicated ANOVA, things will almost always be written in this form, okay? And then you can, in this way, you can add different taus for different groups and things like that. Okay, but
does this crunch down the confound factor?
yeah, you know, so statistics cannot, in of itself, explain confounding factors. Okay, that requires someone who has some knowledge of the subject. All statistics can say is that these two things seem to be linked. It cannot establish cause and effect, things like that. So somebody who knows something about the subject will then be able to design a good experiment and try to eliminate confounding factors. But, you know, if you take somebody who has no idea anything, you know, if you take a engineer and have him try to set up a medical experiment, he or she may not know what's related, and, you know, you probably won't have very useful data. So you need to have somebody in the field who knows kind of what should have an effect and what might be related to set an experiment up. And we'll talk a little bit about experimental setup today. Okay, so is this all right? So I'm going to, let's see, save this, and again, this thing. Okay, so let me just, I should do this. Okay. So let's, I'm going to create dot plots for each of these groups. Diet 1, Diet 2, and Diet 3. I'm going to plot each of these. So 8, 16, and 9. 9, 16, 21, 11, and 18. And Diet 3 is at 15, 10, 17, and 6. Okay. And so if we look at, you know, you can, I wish I had some cool way to animate this, but we can imagine these dots, and then suddenly we're breaking them out, and they, you know, they fly across the screen, and we can say, oh, these 3 dots are coming from here, and these 5 are here, and these 4 are over here. Okay. We can ask, well, do they seem to have, would you say overall their respective populations have different means or not? Okay, if we look at the sample means, we see the sample mean for this group is 11. And so I'm going to actually plot that with a little red pencil mark here. Okay. 11. This sample mean here is 11. This sample's mean is 15. And this sample's mean is 12, which is, I don't know, something like right there. Okay. And we can do the grand mean. Let's figure out the grand mean over here. So our grand mean is I would have to do 3 times 11 plus 5 times 15 plus 4 times 12 divided by 12. So where did my calculator go? Okay, 33 plus 75 plus 48. Okay, so my grand mean is 13. Okay, so again, you cannot just do the average of 11, 15, and 12. That will give you the wrong answer. Okay, so 13, I'm going to draw a blue line here to signify the grand mean. Okay. Okay, so we're asking, so here are our sample means. Our sample means are 11, 15, and 12. Is this indication that the respective populations of diet 1, diet 2, and diet 3 are different from one another? That's what we want to know. Okay? Or could the fact that we got 11, 15, and 12 just be a result of random chance and the different sheeps or the different lambs that I got that happen to gain different amounts of weight? Okay, that's what we're trying to establish. All right, and so we're going to break down our variance in such a way. But before we do that, let me just ask you if you guys remember how we calculate variance. So standard deviation squared. Okay. So actually, we should think of standard deviation as the square root of the variance. So how do we get to the variance? Okay, or how do we, Yes, the variance is the standard deviation squared, but how do we get to the variance? Okay, we take the mean. Uh-huh. Exactly. Okay, so we're taking each individual data point and we subtract the mean from it, which gives us its distance from the mean, okay? And then we square that distance, or that deviation from the mean, and then we average them. We add them up and we divide by n minus 1, okay, rather than n. But, so I'm going to just write that up here, okay, of each y minus y bar squared, okay? We're just going to look at the numerator here, okay? So this would be the variance of everything. We're going to just look at this numerator, which is the squared distance from the mean, y minus y bar, and we're going to break it out into two parts, okay? We're going to look at some distance, y minus y bar, okay, or in this case, with the grand mean, it would actually be y minus y double bar. If I were trying to calculate the variance of all of these data points, okay, I'm going to split this difference y minus y double bar into, we're going to take y minus, we're going to say how far is a data point from its own group mean, and how far is that group mean from the grand mean. Okay. How far from group mean, how far is an individual data point from the group mean, and how far is the group mean from the grand mean. Okay. So for example, if we look at this data point here, okay, over here we would just say this guy is 16, the grand mean is 13, so he is 3 units away. Okay. In our case, we're going to break it out. We're going to say this guy is 5 units away from his group mean. He is at 16, and he is 5 units away from his group mean. Okay, but the group mean itself is 2 units away from the grand mean. Okay, and we're trying to explain. We're breaking apart the total distance from the grand mean into these pieces here. Okay. Okay, so let me get rid of this over here. Okay, so I'm going to create a table, and we're going to so we call this the source, being the source of the variation, and we call this the between group variation and the within group. Which is also known as the residuals. And this will add up to our total. We're gonna have a df column, just ignore it for now. And we're gonna have the sum of squares. Okay, the sum of squares being just kind of like the numerator portion of the variance. Okay, so we're going to ignore the n-1 denominator for now. Okay, so the total sum of squares, if we looked at everything, would be each data point, y sub I, and we would take its distance from the grand mean, and we would square that and add them all up. Okay? What we are going to do is we're going to look, say, each data point is different from its own group group's mean, okay? And we are going to add that up for, and the formal notation has two summation signs to say we're going to do it for all points within a group, and then we're going to do it for all groups. There's two summation signs technically to say we're going to do it for all points within a group, and then for all groups. But basically just do it for everyone, right? And then between the groups, we are going to we're going to take each group mean y bar and see how different it is from the grand mean y double bar. Okay? And we would square that distance. And technically also we would do it for all points within a group and then do it for all groups. Okay? But all points within a group will have the same distance for y bar minus y double bar, right? So I can just say I'm going to multiply it by how many points were in the group. Just because, you know, all 3 points in diet 1 will have the same -2 distance. So I can just take this thing, -2 squared 4, and multiply it by 3. I don't have to individually figure each one out, okay? And then I'm going to do it for all groups. Is that okay?
I'm confused about the why there isn't y bar, there's only one in each group, right?
Yes.
I'm lost, sorry.
Oh, okay. So why am I multiplying by n here?
Yeah.
Okay. So for diet 1, I have three points, right?
Mm-hmm.
Okay. So if I'm looking at this one and I'm trying to split up, I'm trying to break out this distance 3 into 2 parts. I'm saying it's 5 units away from the grand mean, 5 units away from its group mean, and the group mean itself is 2 units away from the grand mean. Okay, and I would do that for all 3 points in diet 1. Okay, but this between groups part where I'm taking this -2, it's this distance between the red line and the blue line is -2 for this point, it's -2 for this point, and it's -2 for this point. Okay, and I want to do it for all the points within the group, so I'm going to do that -2 squared, but I'm going to multiply it by 3 for all the points within the group. Okay. Okay. Is that okay?
Yeah.
All right, and then and so, for example, let's just explore this using actual data, and we're just going to do it for diet 1, just because it can get tedious. Okay. So for diet 1, you know, we look at this data point, which is 16. Okay. We're going to let's do the total contribution for the sum of squares. So we're going to say we're going to do 8 minus 13 and take that distance squared. 13 being the grand mean, right? So y double bar is 13. Okay. So we're going to do 8 minus 13 plus the next data point 16. 16 minus 13 squared plus the last one is 9 minus 13 squared. Okay, and so here I have 25, 5 squared, and then 16 minus 13 is 3, so I have 25 plus 9, and 9 minus 13 is 4, 4 squared is 16, so what is that? 25 plus 9 plus 16, I get a total of 50. Okay. and we're going to break this apart into two pieces. So we're going to look at each data point and see how far it is from its own group mean. So I say 8 minus 11 let me write it up a little bit higher. 8 minus 11 squared plus 16 minus 11 squared plus 9 minus 11 squared. Okay, so 8 minus 11 is 3, 3 squared is 9, 16 minus 11 is 5, 5 squared is 25, and 9 minus 11 is 2, 2 squared is 4. Okay, so I have 9 plus 25 plus 4, I have 38 here. Okay, and then the between groups is I'm going to look at this distance between the group mean, 11, minus the grand mean of 13. So there's a distance of 2. And I'm going to square that, and I'm going to multiply it by 3, because there's 3 data points in the group. Okay, and so I have 3 times 4, 12. Okay, so let me just draw a little box around each of these. So the sum of squares due to the between group component is 12. The sum of squares that exist just within the group, the individual differences, is 38, and the total sum of squares is 50. Okay, and this can also serve as a double check, but you don't have to do this. Okay, basically, if you get 12 here and you get 38 here, if you were to do the double check yourself, you will get 50. Okay, but we can see how we're breaking apart this 50, the total sum of squares, into two pieces: the between group and the within group. Okay, and this is how the ANOVA works, analysis of variance. We're trying to break apart our variances into different pieces and attribute these to different aspects of the data. Okay. So we can see how this worked, and it will work for all, if we do it for all 3 diets and things like that. But we're not going to do that just because that'll be a little tedious. This part, this within group residuals, this formula requires that we have the individual data points. Okay, and a lot of times the individual data points are not provided to us. Okay, we might not have them in our, we might only get summary sheets or whatever. Okay, well, with a computer you would probably have it, but we can kind of shortcut this, because does this part look familiar at all if I hid this extra summation sign? Maybe, maybe not. Here, let me save this page, and let me remember the formula for variance. Sum of y minus y bar squared. That's basically what this is, sum of y minus y bar squared. So if you think back to variance being standard deviation squared, that would be the sum of y minus y bar squared over n minus 1. Okay, so I can replace y minus y bar squared with just n minus 1 times s squared. Okay, so another formula for the sum of squares within the group would be the sum of n minus 1 times s squared. Okay, And you do this for all of the groups. Yes?
Why wouldn't we need individual data points for the total sum of squares as well?
You do need the individual data points for the total sum of squares. But when you do the work, you're really just going to go for the between group and the within group. This is because there is the total is going to be equal to the
The other two.
sum of squares between plus sum of squares within. Okay.
So you can sort of circumvent needing.
Yeah, you don't need to do this individually. And in fact, I only did this to demonstrate that indeed these add up. 12 plus 38 equal 50. Okay, and that, you know, these formulas I'm sticking up here aren't just hocus pocus. I mean, it kind of feels that way a little bit, but we're taking the total sum of squares and we're breaking it out into two pieces. Okay. And so now the question is when we break it out into two pieces, is there enough going to the between group to say that the between group variation is significant? That's what we want to know. Okay. Or is it pretty much that all the variance we observe is just because of individual differences? Okay, that's the next question. And the answer is, well, we're going to have to kind of come up with a ratio between the sum of squares and the degrees of freedom. Basically, how much of it depends on kind of the sample size, right? So let me just continue this. Okay. Do you want to save changes to this document? Sure. And let's throw this up here. Okay, so I had source, and so you don't have to rewrite your table here, between, within, or you can if you want. So the degrees of freedom, in the total degrees of freedom is going to be all the data points, n dot minus 1, okay? And the degrees of freedom also have the same property where degrees of freedom between plus degrees of freedom within will add up. The degrees of freedom between the groups is the number of groups minus 1. Okay, so I think that's called, I think it's I minus 1. I'm just going to write number of groups minus 1. Okay. And so if this and this have to add up to each other, the within groups degrees of freedom will be n dot minus number of groups. Okay, and that way when these add up, they add up to n dot minus 1. The sum of squares, which we did on the last page, is sum of n times y bar minus y double bar squared, and the sum of squares within is n minus 1 squared, okay? And the total, you can just say sum of squares between plus sum of squares within. And then we have something called MS, which stands for mean squares. which is the ratio of the sum of squares to the degrees of freedom. And you do this for both sum of squares to degrees of freedom. And at this point, I'm really just kind of waving my hands and just going to say, well, this is what we do with ANOVA without explaining where these tables come from. But the way we're going to decide whether or not the contribution of the sum of squares due to the between component is significant or not is we're going to take the ratio between this thing and this thing. So this is mean squares between divided by mean squares within. And this is known as our F ratio. So we're going, that's what we do. There's no point in calculating F ratio for within, because that's always going to just be 1. But you're, because it's going to be mean squares within over mean squares within.
Sorry, say that again?
You're only going to, so with Way Anova, you're only going to have one F ratio.
Okay.
If you have more terms, let's say you were further breaking out the total variance into more pieces, due to this component and this component and this component, then you would have an F ratio for each of those to try to find the contribution due to that, okay? And then and what we do with the F ratio is we look it up in a table to see if it's significant, okay? F tables are weird. Our book chooses to represent the F table with a series of 10 or 12 tables, or 10 tables, I think. If you go online and you search for F table, it's going to look different from what our book does. All this to say is that when you do ANOVA, it will probably be done on a computer, and the computer will use its own built-in F table, and you don't have to worry about it, okay? And with our book's case, if you know how to use the chi-square table, then you can use the F table for that they provide. I can also show you how to use an F table that you might find on the internet if ever you wanted to do it by hand. But generally, you would just kind of do ANOVA on the computer, and it will spit out an F ratio and also give you its associated p-value based on its internal F table. Okay. I think the key concept behind ANOVA is that we are trying to break out the total variance, or the total sum of squares, into multiple pieces. Okay. And there's always going to be this within, or what we call the residual component, meaning that there's a part, with all of the data that you gather in the world, part of it cannot be explained by your explanation. Okay? So with Way Anova, you are just using one categorical variable. So for example, I'm trying to explain that people have, the part of the reason why people are of different height is because of their sex. Okay? Some males on average are taller, women on average are shorter, so that explains part of the reason why people have different heights. But that doesn't explain everything, otherwise all men would have the same height and all women would have the same height. So the part that is not explained by this very simple model is called the residual. Now someone else might further improve this model and say part of the reason why people have different heights is 1, because of their gender, and number 2, because of their race. Okay, and they might say, you know, on average men are taller and women are shorter. On average, Europeans are taller and Asians are shorter, and you know, this race is different, and et cetera, et cetera, et cetera. And they might try to further explain that. But even then, at the end of the day, there's individual differences. And someone else might try to improve the model by adding all of these extra things to say, part of the reason why people have different heights is because of this thing, because of this thing, because of this thing, but it's not going to explain everything, right? The only way you can explain everything is by coming up with a model for each individual person. And then it's no longer a model, and it's just a detailed listing of everyone. So there will always be a residual part, meaning part of it is not explained by the model you have set up. Okay? And then the question is, are all of the other pieces that you have included, whether it's the sex or the race or any other explanatory thing, are those important enough to include, right? Someone might try to say part of the reason why people have different heights is because of their household income or something, and maybe we have to turn it into a categorical variable for it to work in ANOVA. So maybe we have, you know, upper class and middle class and lower class or something, and it might turn out on average there is a difference or something. Okay, if we looked at all of our data. And the question is it important enough, or is it statistically significant enough to include and say this actually makes a difference, or maybe it has no bearing on someone's height? And whether it's significant or not comes down to the F ratio of the mean squares due to that component versus the mean squares of just individual differences. Okay? So we'll try this. We'll try this out by hand for this data here. Okay, and then and I think that will be it for one way ANOVA. Okay, so let's we'll fill this table out using the data that we have here. Okay, so. Okay, so I've got source, between, and residual. Okay, so the degrees of freedom for between is, what will this number be? 2. I've got a total of 3 groups minus 1 gives me 2. What is my total degrees of freedom going to be? It's the number of data points minus 1, so it will be 11, which means my residual degrees of freedom will be 9. Okay. The sum of squares, what will the sum of squares be? Okay, so I would take, for between, I would take each group's difference from the grand mean being 13. So I would do 2 squared times 3 plus 5 times 15 is also 2 squared plus 4 times 1 squared. So this turns out to be 4 times 32, 36. Okay. And then my residual sum of squares, using the shortcut, I'm going to do 2 times 4.359 squared plus 4 times 4.950 squared plus 3 times 4.967 squared. So let's try this out. Okay, 210. Okay, which would mean my total sum of squares is 246. My mean squares will be 36 over 2, 18. And my residual sum of squares will be 210 over 9, 23.33. And my F ratio is going to be 18 over 23.33. So I get an F ratio of 0.77. Okay. All right. Okay, so now we would look this up in our F table. Okay. And so the F table is a little bit strange, okay? And you would need a numerator degrees of freedom. There are 2 degrees of freedom. A numerator df and a denominator df. And a lot of times this is like nu1 and nu2. Those are our nus, not v's. And so the numerator, you just look at the degrees of freedom for that component. So in our case, we have numerator degrees of freedom 2 and denominator degrees of freedom 9. Okay. And the 5th edition of the textbook doesn't include any F tables, but the 4th edition does. So I'll show you what it looks like in our F tables here. Here it is. Okay. So this is what it looks like in the 4th edition textbook, where they actually included the table, and in the 5th edition they don't. So table 10, critical values of the F distribution, is like 10 pages long, okay? And they have a different page for each numerator degrees of freedom. Okay, so I'm just going to go to numerator degrees of freedom equal to 2 and denominator degrees of freedom equal to 9, okay? And then I look here and I'm looking for my number, 0.7714. And so I see 0.7714 lies over here, which means my tail area would be what? Greater than 20%. Is that okay? So tail is greater than 20%, which means my p-value is greater than 20%. Because, again, my F is equal to 0.7714, which is smaller than 1.9.
0.13?
Oh, I'm sorry, 1.93. 1.93. Yeah. Okay. Wait, was that your question there?
No.
No.
You showed the table.
Uh-huh.
Between, and like usually you go between.
Yeah. So if my F number was 2.3, then 2.3 is between 1.93 and 3.01, and so my tail area would be between 20% and 10%. But in our case, my F is even smaller than 1.93, so that means the amount in my tail is going to be more than 20%. Let me just show you how the F tables in our textbook are very thorough, but I would say not common. Let me just look up an F table online. So most likely, when you look up an F table online, it'll look like this. Okay. How do I zoom in on this? That's not very good. Okay. So in this case, we would look at numerator degrees of freedom 2 and denominator degrees of freedom 9. Okay, and the number it gives me is 4.2565, and this is the F table for alpha equal to 0.05. So basically, it comes down to if your F is bigger than this number, it's significant at alpha equal to 5%, and if your F is smaller than this number, it is not significant with alpha equal to 5%. Okay? So in our case, our F was 0.77, so it's not significant. Okay? This same number shows up right here when looking at this column 0.05. So basically, this table is just the 5% column. And if your F is bigger than this number, then that means the amount in the tail is less than 5%, making it statistically significant. Whereas if it's smaller than this number, your F is not statistically significant.
On the F table, though, can you expand the tail probability and go even farther to the right or to the left if you wanted to?
It depends. So, you know, most physical reference tables, you'll just have for alpha equal to 5% or alpha equal to 1%. Generally, if you find a textbook, it'll just be split, and it'll tell you how big your F needs to be if you want it to be statistically significant at the 5% or 1% levels. Just because the F is you have different degrees of freedom for the numerator and denominator, and so for it to be thorough, you would need a whole bunch of tables, and so they don't like to do that. Again, probably easier to just do it on the computer. Okay, and so actually, let me show you how we might do this on the computer. And now I'm not sure if I broke my computer. I think so. All right, so what I'm going to do is I'm going to say we'll call this column weight, and this will be group, and I'm just going to enter these 8, 16, 9, 9, 16, 21, 11, 18, 15, 10, 17, and 6. Okay. I could label them group 1 and group 2 like this, and group 3. Okay. So I could do this, or I can also label them group A, group B, and group C. It doesn't matter. Okay. The only thing is if you're going to use numbers to label your groups, when you do your analysis in R, you need to tell R these are group labels, not numbers. Otherwise, R is going to look at this and say, these measurements, have one of something. These measurements have twice as much of that, whatever it is, and these measurements have 3 times as much. Okay, because R will see these as numbers and say, oh, this thing had 3 times as much as these guys down here. Okay. Now, if you call them A, B, and C, R knows that these are just labels. Okay. So the command is to say as.factor. Call it a factor, and not. Otherwise, it'll treat it as a number. That's the default behavior. Whenever it sees a number, it's going to treat it as a number. Okay, so anyway, I'm going to just save this as a CSV file on my desktop here. And we'll call this lambs.csv. Yes. And I hope this works. I'm going to just use vanilla R. And so I'm going to say, okay, we're going to call this data. And I'm going to say read.csv. Oh, shoot, I have to set my, maybe I should use RStudio. Yeah, okay. I forgot. I have to do a... Okay, that's encoding row names, strings as factors. Okay, that's fine. All right. All right, and now I'm going to do lambs $group. Oops. Is as.factor lambs $group, okay? And this will reassign the structure of lambs, okay? Now, I should have shown it to you what it was before. But so str is giving me the structure of lambs, and you can see weight is an integer, and now that I said as.factor, it says group is a factor with 3 levels, 1, 2, and 3, okay? All right, and so to do ANOVA, it's very simple. I just say AOV, and I want to do lambs $weight. Oh, I'm going to store this as model. Lambs $weight tilde as explained by lambs $group. Okay, AOV for analysis of variance. And I hit enter, and it's done. And so we want to know what happened with the model. Okay, and so I ask for a summary of the model that we just built. Okay, and we can see this is the exact table that we produced by hand, right? It doesn't bother with the total thing. And we see, okay, the p-value is 0.49. and there you have it. Okay, I think if you just type in model, it says these are the residuals, and that's what we get. Okay, but you ask for the summary, and it gives you the ANOVA table that we produced. Okay. And again, in our class, we're only covering one Way Anova, which is the simplest form where you have one categorical variable trying to explain a numeric variable, the variance in a numeric variable. So let's, okay, let me also just create, what's it called, strip chart of lambs $weight as explained by lambs $group. Okay, so this is this thing here is our dot plot that we produced here, right? So it's these 3 columns here. It's just turned on its side. Maybe there's an option to make the strip chart vertical. vertical true. Let's okay, so let's do strip chart vertical true. Okay, so this is the same strip chart that we, or dot plot that we produced. Okay, let's say we changed our measurements so that the lambs on diet 3 gained a lot more. So I'm going to just add 10 pounds to each of these measurements: 25, 20, 27, and 16. Okay, so I'm going to save this. And we'll re-import our data set. I'll call this lambs 2. Okay. So yeah, so if I show you structure of lambs 2, you can see group right now is an integer, so I just need to reassign that. Lambs 2 $ group. We want to be as dot factor lambs 2 $ group. Okay. Now, if you used character labels for the group like A, B, and C, you don't have to go through this step. It will understand that it's as such. Okay, so let's do let's create the strip chart now. Strip chart lambs 2 $ weight as explained by lambs 2 $ group, and we'll do vertical equals true. Okay, and so we still see variance, and the question is this group different enough to say that the mean of the population is different? Okay. Oh, I guess one thing I don't know if I made clear enough is that when you do one-way ANOVA, the null hypothesis is that all group means are the same, and the alternative is that at least one is different. But notice it doesn't specify which one is different. It just says at least one of the groups is different. Okay, so you have 3 groups or something, or 10 groups. All it's going to say is, yep, at least one of these is different, and it's not going to tell you which one is the different one. Or it could be that 3 are different from the rest or something like that. It doesn't tell you which. It just answers the question, do all the groups have the same mean, yes or no? That's all it's able to answer. Okay. And I'll get into the problem multiple comparisons in just a little bit here. So here's our strip chart. So let me just do the AOV. We'll call this model 2, and this will be okay. And so with under model 2, we see our F value is now 4.771, and that produces a p-value of 0.0387, which means it is significant at the 5% level. Okay. So triple star means it's significant at the 1 in 1,000, 1/10%. Double star means it's significant at the 1%. Single star is significant at the 5%. Dot is significant at the 10% level. So you get little codes here. So this says, even though you only have 4 data points and in a total of 12 data points, we found something significantly, statistically significant. Okay, but again, it doesn't tell you which one it is. Okay, and all you can do is look at the data and just say, well, I suspect it's this one. Okay. And if you suspect it's this one that's different, then, and you want to prove that, then you have this issue called the problem of multiple comparisons. Okay. Okay. Okay, so one Way Anova has the hypotheses null, all groups have the same mean, and the alternative, at least one group is different. Okay. It will not specify, even with a significant result, which group is different. Okay, so you could then do pairwise comparisons between groups. Okay, so one possible solution is pairwise comparisons between groups. Okay, so you can reduce everything down to basically a t-test. You can do essentially multiple t-tests. Okay, so for example, you could do test 1 will have the null hypothesis mu1 is equal to mu2, and then test 2 will have the null hypothesis mu1 is equal to mu3, and test 3 will have the null hypothesis mu2 equal to mu3, with the alternative that they're different for each of these. Okay, and with three groups, it's not too bad. Okay, but if you had a fourth group, okay, then then it's the question, how many, in a room of 4 people, how many handshakes will there be? And you would have 6. Okay, and then with 5, if you had 5 groups, then it jumps up to 10, and then with 20 groups, you have all of these things, right? And if you had 20 groups, then it becomes 20 choose 2. And how many handshakes are there? I don't know, 20 choose 2. Then it becomes 190. Okay, you'd be doing 190 t-tests. What's the problem with doing 190 t-tests? And it's not that it's a lot of work, okay? Because with a computer, it's not that much work to do. I mean, it's more work than doing one, but it's not too bad, okay? Because you're not going to be doing these calculations by hand. So what's the problem with doing 190 t-tests? Mu1 versus mu2 versus mu1, and mu1 versus mu20, and mu2 versus mu16, and mu3 versus mu18, or whatever. Okay, you'd have 190 t-tests to perform. What do you think the issue there is going to be? It comes to our significance level, okay? So remember, if we choose a 5% significance level, okay, alpha equal to 5%, that means what? We reject the null hypothesis if the probability of getting our result by random chance is less than 5%, okay? And that means our risk of type 1 error is 5%, meaning
95% confidence.
well, it means 5% of the time we will reject the null hypothesis even if the result was just a result of pure chance. Okay, so we're running the risk of making basically a false rejection 5% for every single test. Now I'm doing 190 of these, okay? How many results would we expect just from random chance alone? How often am I going to reject the null hypothesis? About 5% out of these 190 things, right? So that means, 9 or 10 of these things are likely, I'm likely to reject the null hypothesis 9 or 10 times just from random chance alone, or something in that vicinity, just because I did so many t-tests. Does that make sense? Okay? So, because every time I'm running a t-test, I've got a 5% chance of a type 1 error. And if I'm doing 190 of these things, I'm almost certainly bound. It's almost, it's almost guaranteed that at least some of these rejections will be false. Okay, there's actually a very good XKCD comic on significance. Here it is. Okay, so it says jelly beans cause acne. Scientists investigate. And it says we found no link between jelly beans and acne. P, with P is greater than 5%. That settles that. It's only, I hear it's only a certain color that causes it. Scientists, okay. And then so they said, we found no link between purple jelly beans and acne. We found no link between brown jelly beans and acne. No link between, all of these things. And then here it goes. So all of these say we found no link, and it's all of these different colors. And it says we found a link between green jelly beans and acne. And it goes, whoa, P is less than 0.05, and everything else is no, 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 no. And then now the news says green jelly beans linked to acne, 95% confidence, right? This is the type of risk that you run, that you might make doing statistics with a significance level of 5%. And if you do multiple comparisons, you're essentially running a whole bunch of tests like this, okay? And it's almost certain that one of these you're going to reject the null based on random chance alone, okay? And this kind of stuff happens, right? You do a study, and then maybe you find some statistical result, but it could be just random chance here, okay? Okay, so anyway, let me write all of that down. Multiple comparisons, say, and then if you have 20 groups, you will perform 190 pairwise t-tests. Or, I shouldn't say pairwise. 190 t-tests between the different groups. Okay. If alpha is equal to 0.05, then you run a very high risk of committing a type 1 error after, so many t-tests, okay? Or I should just say so many hypothesis tests, really. So Way Anova helps settle that by just you have whatever significance level it is, that's the significance level. Okay. Okay, so let me just briefly talk about the other forms of ANOVA that we are not covering, but exist. Okay, and that would be the one-way randomized block design. Okay. So in this case, each data point, yi, is the combination or the result of the grand mean for everybody, a group mean, plus, or a group effect, plus something called a block effect, plus a residual. Okay, so now we're including a second piece. Okay, we're saying people are different because of this thing and something else, plus the residual. Okay, and then so your analysis, and we're not going to get into it, but basically your source will have the group, the block, and the residuals. Okay, and then you've got the df and sum of squares and et cetera, et cetera, et cetera. We're not going to get into the formulas here. Okay. Why are they called blocks? Okay, these are we do the block design generally if the second thing that we're accounting for in our model is something that we're not really interested in. Okay, maybe it's the effect. We're already aware that this effect exists or something, or maybe it's something that we cannot control for. Actions that we cannot control for, something that is a little bit out of our control when we do our experiment. Okay, so for example, maybe we're interested in maybe different fertilizers for plant growth. Okay, we want to know, here's a plant, we're looking at, little beans here. Okay, and we want to know what affects the growth. Okay, and so we're going to look at maybe we have 3 different fertilizer products that we're hoping promotes growth, or maybe 2 fertilizer products and 1 control. Maybe we'll do that. 2 fertilizer products and a control group. Okay, but let's say our laboratory where we are doing this is a top-down floor plan. Let's say there is a window here, okay? And for whatever reason, we can't get all the plants here, okay? And so maybe we can line up 2 plants here, and we're going to get maybe it's going to look like this. Okay, we have a total of 12 plants, okay? But, maybe these will have the most sun, and then this will have some sun, and these plants will get the least amount of sun. Actually, this is not going to be, let's just, I'm going to delete. Wait a second, what am I doing? Sorry, I think I need 6 in each of these things for it to be a proper 2 products in a control group. Okay, so the worst, so I'm going to have 18 plants here. Okay, this is more than I expected. But the worst design would be to put, you know, fertilizer 1. This would be bad design, okay? So let me put this in red. Bad design. We'll do fertilizer 1, fertilizer 2, and control over here, okay? Because at the end of the experiment, with bad design, what we might find is that the F1 grew the most, and control group grew the least. Okay, so does this mean fertilizer 1 is the most effective and at helping the plants grow? And the answer is no, because the difference that we observe here could very well simply be a result that fertilizer 1 got the most sun and the control group got the least amount of sun. Okay? So that would be bad design, right? Our result, this would be confounding factors, right? The amount of sun, okay, our factors fertilizer and sun are confounded. Okay, we cannot distinguish between the effect of the fertilizer and the sun. Okay. A purely random design will just randomly assign the fertilizers to each of these things, okay? But because it's random, it's still very well possible that maybe we get more fertilizer 1 in this one and more control in this group, just because it's random assignment, okay? So we have what we call the randomized block design, is that we establish most sun, sun, sum, and least sun as blocks. And so this would be random block design, is that we would say within this block we're going to make sure we have 2 fertilizer 1, 2 fertilizer 2, and 2 control, okay? And then we randomly assign those to these plants. And then over here we say the same thing. We're going to have 2 fertilizer 1, 2 fertilizer 2, and 2 control. Randomly assigned among these 6 plants, and 2 fertilizer 1, 2 fertilizer 2, and 2 control, also randomly assigned here. And then in our analysis, we take into account the fact that some of the plants got more sun and some plants got less sun. We take that into account into our analysis, and it will probably be significant. And then, if after taking into account the effect of the sun, we may or may not see an effect due to the fertilizer or the control. Okay? And so the randomized block design will help us determine if the fertilizer plays a role in plant growth. Is that good? Okay. Yes?
In our lab, I think they mentioned something about using random block design, like a 4 to 6, and I wasn't really sure what that meant.
4 to 6.
Yeah.
I'm not sure either.
Like,
this was with the
it was with like
the St.
kids of
John's Wort
80.
one?
Yeah, it was like it was right before they mentioned that they had I guess they had a pharmacist put the medicine and the placebo in like the same containers, but first they mentioned that like they used like a block design 4 and 6.
You know, to be honest, I haven't read the article recently, and so I don't quite remember right off the top of my
I
head.
wasn't sure if we needed to know what that meant. I didn't mention it in my answer.
Yeah, it's probably okay. Huh? What?
I just got what she was talking about. I thought she was talking about some lab in a different class.
Oh.
An actual lab. And I was like, what?
So,
no, I get it. I don't remember that part.
I'm sorry. I'm sorry. I don't remember that aspect. I know they filtered out a bunch of people and stuff, but yeah, I don't remember that part off the top of my head. I'm sorry.
But would for like a medical experiment, would the equivalent of this be something like, all right, we give like, you know, we have a group of people and we make sure that like the same amount of like the old people get the placebo, the same amount of like.
Yeah, so they do what they like baseline comparisons or demographic comparisons between treatment and control, just to make sure that treatment and control are kind of similar to each other. It may not necessarily be a blocked design, but when they do the random assignment, they might do some checks just to make sure the random assignment is random enough. Okay. Just because random assignment, it is possible from random assignment that all the old people end up in the control group and all the young and healthy people end up in the experimental group or something like that. And that would be a problem, right? Because you'd say, oh, everybody ended up being way healthy in the experimental group. This is proof that it works.
Isn't that why they get like a randomization code or something like that? That's supposed to
Yeah, so they try to control for that and stuff like that. And they could do a block design. Block design means they're forcing these numbers into the different groups or different blocks, whereas just purely random with kind of a check to make sure is not the same. Design of experiments, gets really into all of these considerations. We don't have time, or our class just isn't meant to go that deeply into it. The book talks about it a little bit in the sections and stuff, but anyway, it's at least something to consider. This is the one-way randomized block design. Okay. Yeah, all right, and I'll go to the other one, and this is a two-way factorial design. And in this case, we have each data point is the grand mean, the effect of group 1 plus the block plus what we call an interaction and residual. So was this basically effect 1, whatever that is. This is effect 2, and this is called an interaction. And this is the residual. So here there are still two effects, but then we also take into account an interaction. So maybe I don't know, you want to know the effect of being I don't know, in the car versus out, I don't know, you're measuring something on temperature or something, okay? And then you say, well, what's the effect of being inside the car versus outside of the car? What's the effect of being in the sun versus outside of the sun, okay? And so what you'll see is that, maybe being in the car is warmer than being outside, okay? And then being in the sun versus being in the shade, it's warmer to be in the sun than in the shade, okay? But what you might see, and so, maybe car versus outside, it's a 5-degree difference, and sun versus shade, it's a 10-degree difference or something like that. And so if there were no interaction, the effect of being in the sun and in the car should be a total of being plus 15 degrees versus being outside in the shade, right? You would just kind of add those two together. But what you might find is that being in the sun and in the car maybe adds 30 degrees or something, because the effect of the sun and the car together, you know, create this like greenhouse effect where it gets really hot inside the car or something, okay? And so there's an interaction between the two factors, being in the car and being in the sun, maybe works together into creating even more heat than what they would do individually or something like that, okay? Or you might find the effect, the interaction being that they cancel each other out in some other circumstance, okay? So a two-way factorial design takes into each own individual effect plus the possibility of an interaction. In some cases there is no interaction. The interaction is not significant. But in other cases it is significant.
It's an interaction between the two effects? Or, like, well, not between the two effects?
Yeah, between the two factors or effects or whatever you want to call it, okay? So, and so a two-way factorial design takes that into account, okay? And then you can have more factors, and you know it's just called a factorial design. You know, if you have 3 effects or say, and you take into account every single interaction and things like that. And that's what, and it can all be analyzed with Anova and whatnot. Okay. I had a lab that I was going to assign, but I didn't. I wasn't too much of a fan of the lab, so I was going to change it and have you guys do another lab, but I didn't finish it in time, so I'm not going to assign it. Okay, I'm not. So no lab this week. However, I did come across a great article on 538 on Science. Let's just go to 538. Where's the article here? Oh, that was not the effect that this article I was looking for. Science isn't broken, okay? Okay. So, anyway, I highly recommend reading this article, okay? If you're not offended by a few foul words in there. And, well, 538 is a great website. I don't know if you guys are familiar with 538. Run by statistician Nate Silver, who started off doing baseball statistics, became well known for that, and then and in 2008 he became super famous, or obviously not super famous, but he gained national attention because he correctly predicted the outcome of the 2008 presidential election, predicting how every single state, each state would fall based on the polls up to that time. And it was based on what he knew of different polling organizations, whether they have a slight bias towards the left or toward the right, and so his model kind of corrected for that and gave certain polls more weight and other polls lesser weight, and kind of created this average, and he correctly predicted every single state, including the fact that Missouri would be too close to call on election night, and indeed it was too close to call until several weeks after. But it was moot because Obama had enough electoral votes, and his prediction was also just as good in the 2012 election, and so he's become a respected authority on.
At what point does he make the predictions in advance? I mean, how close to the election does he make them?
So he constantly updated his polls as new figures, or his prediction as new polls were released. So, but basically, 2 days before election day, he had kind of this finalized map, or a day or two before election day, and it was like, this is how it's going to go, and it went exactly the way it was, which was kind of like a win for statistics, and a win for Nate Silver himself. So
This is Science Magazine?
this is 538.com. So he has a bunch of different things on politics and sports. The sports section is probably the biggest one, but
538 a reference to baseball stats?
538 is a reference to the number of votes in the Electoral College, each state getting one for each senator and congressperson. 538, there's a total. You need 270 to win. So, because it's he created his own political blog called 538, and it was about the Electoral College votes, and that. So anyway, if you're interested in that kind of stuff, I definitely highly check it out. But read the one, Science Isn't Broken. It's a great article. Okay. So, okay, we'll end there. And, well, unless there are any questions.
Yeah.
Yes.
In the F table,
Uh-huh.
and then the fifth edition book, we have the F table then, right?
Yeah, if it says use the F table, don't worry about it, okay? I'm not on the quiz, I'm not going to ask you to use the F table. I didn't include that. The most I'm going to ask you is what's the numerator and denominator degrees of freedom that you would use, or something like that, which is really easy, right? So, okay. Okay.